Having looked at Planck and quantization and Einstein and the photoelectric effect as certain aspects of quantum mechanics, let's return to talking about light. We know that in the visible spectrum of light, we have the rainbow of colors, Roy G. Biv, and that any source of white light, probably the most common version of that is going to be sunlight, but any light bulb that uses a heated metal filament is going to produce white light. And if you filter that through a spectrum or a diffraction grating, it's going to separate the combination of colors that produces white light into the individual colors of the rainbow. Of course, you would know this if you have any familiarity with iconic album covers. Pink Floyd's Dark Side of the Moon has this iconic image of the white light coming into the prism being separated out into the rainbow. Or if your grandmother has one of those crystals that like hang on the sliding patio door, sunlight comes through at whatever time of the day and you get a spray of rainbows all over the room. That crystal is just another form of prism. Well, why does this matter to us? Well, we know that from the off-by diagram that there are only certain energies that electrons are allowed to have within an atom. This is the quantization of electron energies. And of course, we learned from Planck that all energy is in fact quantized into specific wavelengths. But if you give that electron some energy, and you can do this by running an electric current through that sample of matter. You could set it on fire, all kinds of ways you could give it energy. But when you do, it's going to absorb that energy, and then the electron is going to go to a higher energy level. This is called an excited state. And an excited state is hard to maintain. Nature doesn't like high energy. So that electron might fall down to a lower energy state. And when it does that, it's going to give off light. It has to give that energy back somehow, and it gives it off in the form of a photon. Of course, that electron could have fallen down to that energy level or that energy level. Any drop in energy is going to be favorable under these conditions. Typically, when we have energy drops from a higher energy level down to the second energy level, we get visible light. So here we have potentially red light. If we drop down from the fourth energy level, we might get green. From higher, you might get purple. If you have this sample of matter and you can see this process take place, then you're talking about billions and billions and billions of atoms. So they're constantly giving off all of the possible colors of photons. And so what you're going to get is you're going to get some kind of combination of those colors. And one of the ways we do this in what are called spectrum tubes. So spectrum tubes are glass tubes that have been evacuated of all air, and then we fill them with a pure sample of some gas. So here you have several different substances, several different elements. And this is typically the process, by the way, that you get neon signs. The traditional color of neon sign is that orange because it's in fact neon. But other colors of neon signs are really not neon. They're just different gases. But because each of these elements starts with a different arrangement of electrons in the off-by diagram, each of them gives off a different combination of colors. Neon's electron transitions tend to favor electron or energy transitions within the red and kind of yellow range, which is why you get that kind of orange glow from a neon sign, whereas argon, as you can see up there, tends to have more of its energy transitions taking place in the kind of purple range. If we were to take the light from any one of those spectrum tubes, though, and filter it through a prism like we did with the white light, since it's not all colors, it's just going to separate into the different colors of photons that particular arrangement of atoms can give. And this is known as an atomic emission spectrum. And because every atom starts with a different arrangement of electrons, every atom gives off a different spectrum. And they are, in a sense, kind of a fingerprint of that element. We know that as we go from purple to red, that we're increasing our wavelength. Red light has longer wavelengths than purple. We know that increasing wavelengths mean decreasing frequencies. And so lower frequency, increasing wavelengths do equal lower frequencies. Lower frequencies equal lower energy. And so as we're moving from left to right, our frequencies are in fact increasing, which means we're increasing our energy. All right, well, what does this mean for us? Well, because these atomic emission spectrums exist, that is some of the evidence we have for the fact that this quantization of energy within the atom is in fact a thing. And here's why. If electron energies were continuous, and we were to take this electron in this energy diagram, and we were to give it energy, then that electron could have since go anywhere it wanted. It can gain any amount of energy, and then when it fell back down, every possible frequency of light would be given off. And if you were to separate the light given off by that substance through a prism, you would get a continuous spectrum. So if heating a pure element in a spectrum tube and then analyzing the light gave you a continuous spectrum, that would tell you that an electron could have any possible energy. Because again, that sample would be billions and billions of atoms constantly gaining and losing and gaining and losing and gaining and losing and giving off a constant stream of photons. And if all wavelengths were possible, then every atom should give a continuous spectrum. But they don't. Atoms give lined or emission spectrums where only particular wavelengths are given off by particular gases. And so that electron could go there, it could go there, it could go there, and then it could fall back to any of the energy levels below. But only certain energy transitions are in the visible spectrum, and only a couple of different wavelengths are given off by any particular sample. And again, that emission spectrum kind of acts as a fingerprint. What we also know is if we can measure that wavelength with the when we analyze the spectrum, we can convert that wavelength into a frequency. And if we know the frequency, I can tell you all of the energy transitions that are taking place there. Another kind of application of this that's super useful. So if we look up here in the top right, we're talking about emission spectrums come from heated gases. So you're talking here about the spectrum tubes. And so different samples have an electric current run through them. Their electrons increase energy. That energy drops. And then you give off these line spectrums of where the electrons are changing energy. If you have a continuous spectrum, that comes from a white light source. So again, that could either be sunlight, it could be a light bulb that has a heated filament. If that light source is behind a sample of gas, then, for instance, you might have a situation where you have a star behind. You have a star behind a sample of gas, like in like a nebula, and on Earth, you have yourself a telescope that has a spectroscope on it. You can look at the light coming through that nebula, and what's going to happen is the gases in that nebula are going to absorb the energy from that white light source. And so then when you look at the light passing through the cool gas, you're going to get what are called absorption spectrums. There's going to be blanks where those lines would have been in an emission spectrum. And so we can figure out what are in various astronomical objects by using this spectral analysis. So for instance, if that hot gas is hydrogen, and then we look at a spectrum of a nebula with a star behind it, and we find all of those lines missing from hydrogen, then we know there's hydrogen in that sample. Okay, so here's what a spectroscope, which separates light out into its individual wavelengths, looks like. So not only does the light get separated out into these little bands, but a spectroscope actually has it scaled so that you can measure wavelengths. And this is wavelengths in hundreds of nanometers. So that's 400 nanometers, 500 nanometers, 600 nanometers, and 700 nanometers. So what I'd like you to do right now is see if you can take a reading for the wavelength of that band of light that I have here just past the 6. Make sure you record it to the right number of significant digits, and make sure you record the units. Okay, so hopefully you paused the video, you took a break, and you tried to take your measurements. Again, if this is 600 nanometers and that's 700 nanometers, every line here represents 10 nanometers then. So if the lines go to the tens place, you have to go to the ones place. So hopefully you got something like 6.18, 6.19 nanometers. Again, the last digit is estimated, so there could be some variation there. Okay, so nanometers are 10 to the negative ninth meters. These are very, very short wavelengths. So if we convert this to scientific notation and meters, we should have gotten 6.18 times 10 to the 7th meters. Okay, once you have a wavelength, you can use the following equation to find frequency. So again, go ahead and pause the video, run your calculation here and tell me what the frequency of that light is. Okay, hopefully you paused, did your calculations. Round off for SIGDIG, should have 3 significant digits, and you should have gotten 4.85 hertz. Again, if your measurement was 619 nanometers, then you're going to have a slightly different value there, but it should be pretty close. All right, once we know the frequency of the light, now I can use Einstein's equation from the photoelectric effect to find the energy associated with that wavelength. So energy is Planck's constant times nu. Planck's constant is 6.626 times 10 to the negative 34th joules times seconds. So again, go ahead and pause the video. See if you can do the calculation for energy here. Okay, if you ran the calculation, you should have gotten 3.22 times 10 to the negative 33rd joules. That's a very, very small number, but we're talking about the energy of a single photon. So it's not surprising that that's a fairly small amount of energy. But that's how we run through those calculations. We take those measurements to find particular bands of light. We can measure their wavelengths with a spectroscope. After filtering the light through a prism, we can convert the wavelengths to frequencies, the frequencies to energy, and that's what helps us build the energy diagram for the Aufbau arrangement.